Okay. My name is Robert Barnes. As Werner mentioned the other day, we're passionate about measuring, and so I suppose my title should be Director of Measurement or Measurer-in-Chief or something like that for Amazon Web Services. The topic for today is best practices for benchmarking and performance analysis in the cloud. I realized as I put this talk together, I had a couple objectives, but I also realized what my problem is. I should probably have a lot of therapy for this, but I seem to have an attraction for measuring things. And maybe from a professional perspective, it harkens back to my first paid computing job, which was working in a metrology lab. If you're not familiar with what that is, it was at an aerospace company that had to measure things with very strict tolerances, and all of the equipment they used for measurement needed to be calibrated against NIST standards. So I was coding with PDP-8 and PDP-11s that did automated calibration of oscilloscopes and that sort of thing. I won't tell you how long ago it was. There were some slide rules at the time. I'll leave it at that. However, I'm going to actually start with a pseudo benchmarking demo. Now, any of you who've done benchmarking know that demos and benchmarks don't really mix. I've had to do them live, and it really can be painful. But I want to start with a question of the audience, and I'll do a quick survey on the answers here. There are a number of devices that I happen to have on my desk. I have most of those here right now. And they all can be used to measure. How many different ways do you think these can be used to measure? How many people think it's 5 or less? Just raise your hand. Okay. 10 or less? Okay. 15 or less? 20 or less? More than 20? Okay, we're on the right track. There are at least 20 ways to use these devices, and I'll illustrate quickly. Don't worry, I'll make this relevant. You don't have faith in me, but so this tape measure. You could use the width of the tape measure. You could use the height of the tape measure. You could use the length of the tape measure. You could actually use it as intended. You could use the width of the tape measure, or, my favorite, you could use the thickness of the tape measure to measure. Now, prior to starting, I asked some brave volunteers to assist me in this demonstration. I had 4 methods of measuring. I had this wonderful laser-based, accurate to 1/16 of an inch measuring tool. Got to have one of these. Not that I'm passionate about this at all. A regular tape and a ruler, and the fourth approach was measurement by estimate. And I asked these brave volunteers to measure this stage. The measurements that I got were 16 feet for the estimate. The digital tape measure came in at 24.17 feet. The tape measure came in at 24.125 or 24.25. The ruler came in at 23.25 feet. So what does that tell you? All of those measurements were measurements of the stage. And if you didn't know there were other ways of measuring, how would you know which one of those was accurate? In fact, the first time I had bought this wonderful tool and used it, the first thing I did was calibrate it against the tape measure, because I wasn't sure how to hold it. Think about it. This thing has an emitter here, and it measures here, but I didn't know the way they designed it, whether it started measuring from the bottom of it or from the top. And so it took a little bit of a while before I could trust this tool. This is where I bring it in. There are many, many ways to measure performance. You have to understand how the tool is measuring and how relevant that measurement is. And if you're using a tool for the first time, I recommend using more than one tool to see if you can correlate the results and make sure that they are meaningful to you. Before I get into actually talking about measurement, I want to give a little bit, I promise, a little bit of background on cloud benchmarking. First, I have to start by saying the best benchmark is your own application. I know you hear that all the time, but the reality is when you use some other way of measuring things, you still have to tie back what that thing tells you to your actual application. Or put another way, how many people admit to running a benchmark in production right now? You're running a benchmark in production. That's your business, is running the benchmark. Probably not. I realize that was a somewhat sarcastic question. But the point is there's usually some application that you're really running, and sometimes it makes sense to use something to help you tune it or baseline it or something. You still have to tie back what you measure to your actual application. In all benchmarks, you're typically dealing with two types of measurement. Absolute measurement, in this particular case, the measurement of the stage. We're looking for an absolute measure, or relative measure. I could tell you that for those 4 measurements we had, the mean, the average of those measurements was 21.88. And the standard deviation was 16%, given the wide variance. Those relative information can sometimes help tell you how accurate your measurement device is, and can also help you pinpoint whether artifacts you're measuring are things you're trying to measure as opposed to the way you're measuring. Now that wasn't what I wanted to do. Okay, help me with button dyslexia here. Is it going through stages? Sorry? Oh, is it back to 1? Is that what it did? Okay, I can get it. I can get it. Yeah. See, if you don't know how to use the tools, then you're really in trouble. We're good. Okay, absolute versus relative. Benchmarks are typically going to give you either a fixed amount of work and you measure how long it takes, or they're going to give you a fixed amount of time and you count how much work happens within that time. It's important to understand which kind of test it is, because, for instance, when it's a fixed amount of time and you're counting how much work gets done, higher is better. When it's a fixed amount of work and the time is what you're measuring, lower is better. I've actually seen published results where people got that wrong, and they touted results that should have been considered in terms of lower is better. They got it backwards. What's different about benchmarking in the cloud? There are 2 broad categories of what's different that I really need to point out. The first one is there are typically a few more layers of abstraction than what you would be doing if you were doing it on premises. What do those layers of abstraction mean? Well, on the positive side, it means you're not wrestling cables. You're not calling someone up to say, hey, can you configure this for me? You know, you're provisioning very quickly. The flip side of that is because there are more layers of abstraction, there's more likelihood that you could have some sort of variability. So as a rule of thumb, you typically need to run more iterations of your test in order to quantify variability and make sure you understand where it's coming from. Last point before we get into actual measurement, I promise, use a good AMI. That may sound like a strange recommendation. What do you mean good AMI versus bad AMI? Well, to illustrate this, I ran some experiments on the exact same instance type using the exact same binaries, using all of these AMIs except for one were CentOS 5.4, the same distribution, and I got dramatically different results. It turns out that the differences were primarily because the kernel in the first 3 AMIs was an old kernel. It was a Fedora kernel from 2007. And that particular kernel does not handle multiprocessors well. How did it manifest itself? Well, theoretically, all these results should have been pretty similar, and I mentioned using 2 tests to calibrate. What I did here was also run Ubuntu 12.4, which was the latest release, the Amazon Ubuntu release at the time I did this test. And it came in pretty close to the AWS CentOS 5.4 release. So I knew that those results were probably reasonable and these other ones were not. When I looked at the coefficient of variance, if you're not familiar with that term, that's dividing the standard deviation by the mean. It gives you a relative percentage of variation, which is a great way to look at variation. And you could see there was almost 50% variation in the 3 bad AMIs. What does all that mean? In general, if you're using an Amazon AMI, it's been tested, we've done a lot of work to make sure it's okay. If you're using another AMI that came from somewhere else, even if it's your own AMI that has been around a while and you keep using it, it's worthwhile to go back and make sure it's still a good AMI, because they can get out of date over time, and you need to keep them up to date. Going into actual measurement. I'm going to cover CPU, memory, and disk. I could probably spend at least an hour on each of those topics, but I wanted to try and cram in as much breadth here and maybe leave time for a few questions. If not, I promise I'll figure out where we can do the questioning afterwards if you still want to drill me on questions. But this first one, let's say hypothetically that you have an application that you're running on premises, and what you want to do is find the best instance to run that same application. The first question you have to ask yourself is, what is best? How do I know it's best? Best sounds like a great term, but there could be absolute performance, there could be price performance, there could be other parameters. You need to be able to answer the question best. But a very methodical approach here in trying to do this, I get asked this a lot, is let's say that you don't have a benchmark for your application. It's complex to set up. You don't have test data. You don't have security set up. So you want to use some proxy. So you find a synthetic benchmark, and for CPU I'll do 4. You configure and run that on premises, so you get what we'll call a baseline here. You then use the exact same configuration and scripts, hopefully, to run it on instances. You run those tests multiple times, you look at things like variability, and based on your definition of best, you're now ready to go the next stage, which is deciding which one. So for testing CPU, going through those steps one at a time, we'll choose a benchmark. For the purposes of today, I picked 4 that I tend to see used a lot. Geekbench, UnixBench, Sysbench, the CPU part of that, and did I say UnixBench? Yeah, if I didn't. SPEC CPU, sorry, integer. By choosing these, I'm not saying these are the only ones you should consider. I'm not endorsing these as the best ones there. I'm just trying to illustrate how you would go about doing this and some of the strengths and weaknesses of using them. The first question you have to ask yourself, particularly with a benchmark you've never used before, is how do I know I have a good result? For instance, in my example here where I asked 4 people to measure the stage, what I did prior to them measuring the stage is I carefully measured the stage 3 or 4 times from different ways, and I came up with an answer of 24 and 9/16 inches, which is pretty close to where most of them came in. And if you actually look at it, there are 6 panels here, and each of them are 6 feet wide. And so I had multiple ways of saying, yeah, that seems about right. And then I used the measuring tape and so on. But when you're using one of these benchmarks, and if you've never used it before, sometimes they're completely black box. All you do is say, run, and it gives you this beautiful answer. Most of the time, the beautiful answer is in arbitrary units that make no sense to you. It's just a number. How do you know that number is representative? How do you know there aren't things you could tweak on your instance, in your OS settings, if the app supports tweaking in the app to say this is a good result? I should say for people who are practitioners of benchmarking, the first question to teach young engineers to ask is, how do I know when I'm done? Right? Because faster means infinite. Make it faster means you've got job security for life. For these CPU tests, I ran on 9 different instance types. For each of the instances, I launched 10 instances. You get what I'm trying to do there? I talked about quantifying variability. I wanted to look at variability in several ways. And so numbers help a lot. I used the same base AMI, in this case Ubuntu 13.04, for all of these tests. So the first test I mentioned was Geekbench. And Geekbench has workloads in 3 categories. There are 13 integer tests, there are 10 floating point tests, and there are 4 memory tests. I should say this is a black box. It comes as an executable. You can buy the commercial product, which is full-featured, or you can get a free download, which is 32-bit only and has limited functionality. It sets up quickly. It doesn't really take much to set it up. It gives you results in roughly 2 minutes, so it sounds like a dream. It gives you both single CPU and multi-CPU results. And I'm talking about version 3 of Geekbench. Version 2 had lots of problems, and I met with them and I pointed out from a methodology perspective what was wrong. They made a bunch of improvements, and at least based on this testing, it's much better than it was. So speaking of testing, I'm going to show you scripts, and don't worry, there's going to be a lot of stuff here, but I'll break down what's there. The idea is that you can take these scripts The presentations will be available. You can take these scripts and harvest them all you want to help. But when I set out to write a script for benchmarking, the first thing I do is figure out what are the results going to look like and how am I going to incorporate them into analysis tools. Because you can run tests all day, and a lot of times tools like Geekbench will give you human readable reports. But if you're trying to run these tests at scale and automate them, then you need to think about how do I parse the results? How do I stuff them into a database or a spreadsheet? So the first part of this script is designed to name the file, because when you're running tests multiple times, you have multiple results. How do you know which one is which? So naming the file helps me keep track of the metadata about the test. And in this particular case, I use the APIs to get both the instance ID, that's the first blue line, and the instance type. And when I'm running these tests across 9 different instance types, and I'm pulling them all together into one spreadsheet or database, it helps to know what they were so I can do analysis. The next part is actually the running of Geekbench. It's highly complicated and sophisticated. You need hours to train. No, it's very simple. On Linux, the x86 version basically has 2 parameters. The first one is upload or not upload. By default, they will take your results and publish them publicly. If you don't want that, then you may want to say no upload. The second option is whether you're running benchmarks or whether you are doing a stress test. It does not tell you how long it takes. It doesn't report that information. So I wrapped the execution by a start and end capture of the time, computed the time by doing a diff. I know there are lots of ways to do this. I'm just showing a simple and straightforward way to do it. Then I essentially make the output file the combination of the instance type, the instance ID. I passed in a sequence number because if I run the test 4 times, I want to be able to distinguish between each of the tests. And finally, in this particular case, I'm actually putting the time into the file name as well. Why? When I import it into Excel, Excel has these wonderful text import wizards that help you put things into columns, and it just makes it easy for me to do the analysis when I actually go to do the analysis. Finally, pulling the data out. So I use a combination of grep, sed, and awk to pull the results out. I won't bore you by going through line by line. If you're not familiar with those tools, they are must-know tools, at least on Linux, in order to grab data and put it into a useful format. I tend to like to use comma-separated values just because there are so many different tools that accept that format, and so I always figure out how to parse things into comma-separated format value. So I mentioned we would look at results. So these are actual results, and let me walk through what this table is and how to interpret it. So for these tests, for all of these tests, I decided to use a single CPU on a CC2 8X large as the baseline. Since I'm interested in this particular case in integer CPU performance and I'm trying to find the best instance, the absolute values for a tool like Geekbench mean nothing to me. What matters is the relative performance, and so I'm setting the CC2 8X large as 1. Then I have the 1 CPU ratio, which is for each of these instance types the results that Geekbench provided for a single CPU, and all of these are ratios to the baseline, the CC2 8X large. You'll notice that they're fairly consistent with the M2s being slightly lower than the M3s, and the M3s are slightly lower than the C3s, the new C3s. That's completely understandable. The C3s have 2.8 gigahertz processors. The M3s are 2.6, I believe. The CC2 is definitely 2.6. I also measured the coefficient of variance. One thing I want you to take away from this, just because the tool reported a coefficient of variance doesn't mean you can say, aha, that variance is in that instance. What you can say is you measured it, and what you have to figure out is where it's coming from. Remember our exercise where we had 4 different people measure this stage, and we came up with a 15% variance? The stage wasn't changing in shape or size. The difference happened to be artifacts of the way the measurements were made. In fact, I should point out, as I mentioned, this digital tool is great, but if you don't understand that it's measuring from the base, you could be off by, I don't know, 5 inches. by assuming that it didn't count that or something like that. So you need to know what it's telling you. Next, the third and fourth columns are the multi-CPU. I call it N because multi was too long and the table got wide. So the multi-CPU ratio, that's running the geekbench number that came out relative to the baseline, again, the single CPU baseline, and then the coefficient of variance. You can notice here that the ratios are higher, and you would expect that when you have more CPUs involved that you would get more results. You'll notice the coefficient of variance is higher. Now, one assumption you could make is that the coefficient of variance is higher because there's more variability when you're running more threads on the instance. You could also assume that the tool itself is less accurate with multiple CPUs, and the variance is coming from there. You could decide maybe it's a combination of both, and I don't know, so I'll have to try and figure that out. What's really important is, as I mentioned, the runtime for this is fairly consistently right around 2 minutes. Now, all of the benchmark workloads that are in Geekbench are publicly available, but Geekbench doesn't provide the source. They don't tell you how they tuned it. They don't tell you what workload parameters. I can tell you from running each of those tests individually that they take a lot longer than 2 minutes to run in a single CPU and a multi-CPU. So they've drastically scaled down the workload, probably trying to tune this to look like something. I'm not sure what they tuned it to look like. But a runtime of 2 minutes is a great way to get a quick and dirty check. Now, I mentioned that I wanted to look at variance from multiple ways. My previous chart had 9 different instance types. On this chart, I'm taking just one of those instance types, the M3 X large. And remember, I mentioned 10 instances were running. Each of those 10 instances ran at least 4 times. So I took the mean and the coefficient of variance from those runs, and I'm showing you here what they look like. And you can see they're fairly consistent in both the ratio to my previous baseline and in the coefficient of variance. It's important to look at variance across tests and within tests. Now, I mentioned earlier that I'm really interested for this particular hypothetical scenario in integer performance. So I pulled out the integer-only portion of Geekbench to compare it to the full benchmark. Remember, it had 13 integer, 10 floating point, and 4 memory tests. I'm only looking at the integer portion. Now, in this particular slide, I can't tell you how long the integer portion took because Geekbench doesn't call that out separately, but it's certainly a fraction of the typical 2 minutes for these tests. I just pulled a subset of the instances to look at this in detail. What you'll notice in just looking at the integer portion is that the coefficient of variance is typically lower for the same sets of results for both the single and multi-CPU variance. The ratios are also different and slightly higher, but we'll come back to that in another slide coming up. Now, UnixBench is another popular test. It's actually been around for a while. It was originally, the byte index is the default when you run UnixBench. And it was originally developed for Byte Magazine as its Unix system test to give people a measure. It has 12 workloads that run 2 times by default. This is a fixed time workload, so what you're counting is how much work gets done in that fixed time, and it takes about 30 minutes. It does have integer, floating point, system calls, and file system calls. It does a statistical combination using a geomean to come up with a relative measure to an ancient SPEC 2061, I believe. It's a machine you couldn't possibly buy today. But when you have a benchmark like this, as long as it's consistently using the same baseline and the results are always measured the same way, those relative numbers should hold. What they mean to your application is another thing completely. One comment about this, it has the source code, it's available as source code. It hasn't been updated since I think 2007 maybe. It does not work by default on greater than 16 CPUs, so you have to patch it. If you go to the Git distribution, you can find the patch for doing that. I've actually seen published results where people said they were testing 32 CPU systems. And I looked at the results and found there were no results for the 32, so I really wondered where they made the numbers up because I knew they hadn't patched the results. So the script for UnixBench, again, I'm using the ID of the instance and the type to create the file name. In this particular case, in order to run the single CPU and multi-CPU, I'm using proc CPU info to get how many processors are exposed. Then a very sophisticated runtime command, it's capital R run. -C says how many threads to use, or how many copies. It's a single-threaded test that you run multiple copies to get a full measure of the system. So this command line says run 1 CPU and then run n, where n is the number of CPUs exposed. Then again, it's always important to figure out how you're going to take those results and put them into an analyzable fashion. So I use a combination of grep and awk to pull those results out and put them into a comma-separated value. Here are the results, again, looking at relative compute. This is for the full UnixBench test. You'll notice that these ratios look slightly different. Again, I'm using the CC2 8x large as the baseline. You'll notice that, for instance, the M2s seem to be almost half the performance of the baseline, whereas in the previous set of tests with Geekbench, they were about 3/4 or 0.7. Which one of these is right? Well, they're running different tests. They're giving you different answers, and you have to really decide for what those tests do, which is more meaningful to your application. Or if there are ways to tweak the test to make it more meaningful. You'll notice in this particular case that the multi-CPU ratio, it looks pretty screwy. It goes from basically 3/4 up to maybe 6 times, whereas in the previous test, it went up, I believe it was about 16 times. The coefficient of variance has some wild results here, even in the single CPU test, but the runtime is always consistently around 30 minutes. Comparing just the integer portion, which is Dhrystone 2 of UnixBench, to the full benchmark, you can see now that for the subset of tests, the single CPU tests look fairly similar. The coefficient of variance tamed quite a bit. The multi-CPU looks very different in that instead of getting a ratio of 6, we're getting a ratio of 15.5. And I can tell you from looking at the source code here, it's the file system and system calls that basically become almost single-threaded. So if you're trying to get a multi-CPU measure and it's a blended result, they really damp down the CPU result. If you cared about CPU only, basically you should ignore the full UnixBench result and look only at the integer portion. The runtime is fascinating here. The integer-only portion, which you can pull out from UnixBench, takes 10 seconds, or 0.17 of a minute. So talk about a quick and dirty answer. 10 seconds and you're there. Again, you have to say, is this test meaningful to me? And how do I want to use these results? Now, SPEC CPU 2006 is probably the most comprehensive of these 4 different test types that I'm showing. It is a competitive test, meaning it has been designed by public committee, the open software group, to be a competitive benchmark where if you want to run it and publish results, there are rules for both how you run it and how you report it. And a lot of those rules were designed to make it a fair and even thing. And they actually talk about how do we prevent cheating and those kinds of things. So it's focused on being used for competitive purposes, but it's a very thorough test. It requires a commercial site license. It's provided as source code. It must be built. And on the positive side, it's highly customizable. On the lots of work side, there are so many things you can do that tuning can take a long time. However, the good news is, because this is a publishable result, the published results are available, and those published results have to include the compiler settings and the configuration settings. So the question of how do I know I have a good result, you can go and look up published results and say, oh, what system type was this? What configurations did they use? Let me see if I can reproduce their results. Now I know I'm starting from a good base. It does take quite a long time to run. It's a fixed work variable time kind of benchmark. And so if you run it in fully reportable mode, depending on how fast the processor is, it can take 5+ hours. 5+ hours for a fully reportable run is a good time. I've seen results longer than 24 hours because it runs a number of tests multiple times and it takes a while. I'm only going to focus on the integer portion. There are 12 workloads. All of these workloads are derived from actual workloads of some sort, but they've been highly tailored to be repeatable and be used as benchmarks, so they're scripted and don't require a lot of, they don't do any disk I/O and they don't require a lot of system services available. For the purposes of a following slide, I want to point out that each of these workloads has a code that designates the workload, so you don't have to spell out the whole workload when you're telling a SPEC CPU how to run. I also want to point out that by default, the full integer workloads require 2 GB of memory per CPU. It's a single-threaded application that to get a full measure of the system, you run multiple copies. So if on the configuration you're testing, you don't have 2 GB of memory for every CPU, you need to do some tweaking to be able to get meaningful results. The tweaking I would suggest is removing 429 MCF, because it's the one workload that requires almost 2 GB. So in the script that I'm about to show you, which for the most part looks similar to the other ones, basically I'm coming up with a file name. In this particular case, SPEC expects things to run in a well-known path, and again, knowing the number of processors helps you decide how many copies to run. Here's the invocation command for SPEC. This looks fairly simplistic, but I have to tell you most of the complexity is in the config file. I'm using a default a file in a well-known place called configs, and it's named default.config, so I simply don't have to type it in. But all of the complexity is in the config file. In this particular case, I'm saying it's a not reportable run. I've tweaked this to take the least amount of time. One other thing I should have mentioned, if you worry about the cost of benchmarking, then the longer it takes to run a test, the more it costs you to run. So anything you can do to shorten the length of time that the test takes to run without sacrificing the accuracy of the test makes it cheaper to run the test. In this particular case, I'm using iterations equals 1. The default is iterations equal 3. So right off the top, I cut the time that it took this test to run to 1/3 of what it would normally take. Secondly, I eliminated the MCF workload. You'll see in the numeric list, if you memorized all 12 of those workloads, that I did not include the MCF workload. That eliminates the 2 GB requirement, so I'm able to run this across the full gamut of instances that I was testing. In this particular case, they have a peculiar file naming convention. I happen to know what that was, and so the combination of gret, cut, and awk helped me pull out of the comma-separated value that they produce the final result that I used to compile this analysis. You can pull out each of the individual workloads and do a lot more in-depth, but we only have an hour here, so I'm trying to accelerate this. So in this particular case, again, using the CC2 8x large as the baseline, you see that the ratios here actually look fairly similar to what we saw, for instance, in Geekbench, where the M2s look to be about 0.7 or 3/4 of the CC2 8x large. The C3s look to be about 8 to 10% better. The coefficient of variance for both the single and multi-CPU runs are actually pretty good. This is, I can tell you from experience, this is one of the artifacts of how much engineering went into building this benchmark to make sure that results were repeatable and that artifacts that you measure are really a result of what you're measuring and not the tests themselves, if run properly. Now, I mentioned this does run longer, and even in this tweaked state, the run times were from an hour to almost 2 hours. It takes longer to run the multi-CPU tests because the way it times it is it waits for all of the copies to completely finish, and sometimes on larger CPU systems, it takes longer. The results are still computed using the same statistical method, but the total time it takes to get all the work done can be longer. The last one, and then I'll pull together a summary of all 4 of these and compare and contrast. Sysbench was designed for DBAs to do a quick and dirty test of a system for its usefulness for MySQL. It has 6 different test categories ranging from file I/O to actually doing OLTP database calls. It's provided in source code format. It must be built. My best advice on this test is it has very, very simplistic defaults. One might say outdated defaults based on when it was developed versus what kinds of systems are available today. And so I highly caution you at using any results with Sysbench that use default values. You'll see why in a minute. The script here is very similar. I won't spend time. I'm figuring out the name of the file. In this particular case, the defaults for doing the CPU tests allow you to specify the max number of requests. By default, it's 10,000. I modified it to 30,000 when I tuned it. And the max primes, it's basically doing a prime number calculation. By default, the max prime is 10,000. And here I set it to 100,000. This is a fixed work variable time. So all it tells you when it runs is how long it took. The challenge here is with the defaults. If you look at the runtimes here, first of all, the results here, using the same baseline, the results seem a much broader spread from 3 up to 25 times. Actually 1.78 to 25 times. The coefficients of variance tend to be much higher than we've seen. But most importantly, if you look at the runtime here, these are fractions of a minute. So for instance, for the CC2 8x large, the runtime for the default CPU test is less than a second. It's a half a second. And if you think about the accuracy, this is kind of like taking my measuring tape and measuring the width of this stage by the thickness of the tape. It's just pretty hard to get an accurate result when the test runs so quickly. And so that's what I meant about the defaults. Now, using my tuned results, you can see that the ratio starts to look a lot more like the ratios we saw before, ranging from a little less than 1 to about 13.7. And the coefficient of variances are better, but still slightly wonky. And from what I can tell, that wonkiness is an artifact of the test, not of the instances. Because remember, I use the same instances for all these tests. And finally, the runtime in this tweaked version is still fairly short. The longest one is about 7 minutes. So you could theoretically use something like Sysbench and play with the parameters till you saw behavior that looked more like your application. My best advice, though, is be very careful with using defaults on this. So in the half an hour or more that we've been diving into CPU measurement, I've given you 4 different ways, actually 6 if you count the variance here, but a bunch of different ways of measuring CPU. The first question I'd ask you, going back to the beginning, is how do you know when you've got the best instance? In this particular case, you'd have to decide which one of the tests was most relevant to you, which tests you trust the most, or which combination of tests. But a few things I'd like to point out. Particularly with UnixBench and with Sysbench, using the defaults may not give you the most meaningful results, and so you need to look carefully at what the tests are telling you to see if that makes sense to you. Secondly, if you look at the tuned results here, they all come in fairly similar. So I mentioned earlier, if you're using tests for the first time, having more than one way of calibrating tests against each other tell you whether you're getting something that makes sense. So you may decide the best test for you to run in this case is the one that costs you the least in terms of getting the test and how long it takes to run it. And it's good enough. If, for instance, using the analogy of measuring the stage, I was trying to make a solid gold cover for this stage. Well, I don't know, I'm just using that as an example, where precision really meant the difference between spending lots of money or not. You would probably want to use that digital measure and make sure you knew how to use it really well to get a really accurate measurement. If you're doing one of these, well, that's good enough kinds of tests, then maybe one of these tests that runs in 2 minutes is good enough. I can't tell you which one is right, but you really have to understand what the test does and what it's telling you. Transitioning from looking at CPU to memory, using a similar approach, except in this particular case, the scenario I'm going to use is I need to find an instance that gives me at least 20,000 megabytes per second. I know that's a critical throughput for my application, and so I'm going to run these tests using several different types of measurement, and I'm looking for an absolute value of at least 20,000 megabytes per second. Same approach, choose a benchmark, run it on premises, then run it carefully on the set of instances you're considering, and then do your analysis. In this particular case, I'm going to introduce one new test called stream, and that's partially true in that if you were really fast and you read my slide on what the tests were in Geekbench, the 4 memory tests were actually variance on stream. In fact, there are 4 workload types in stream I'm going to talk about on the next slide. Then I'm going to use the memory test portions of Geekbench and Sysbench to compare and contrast these tools as a way of measuring memory throughput. Again, using 9 instance types, 10 instances of each one to get a sense of variability, using the exact same instances I used before with the exact same AMI. So stream was developed by Dr. John McAlphin, University of Virginia. If you go to his website, his nickname is Dr. Bandwidth, so that tells you something about him. There have been many, many academic reports based on using this tool, particularly for hardware engineers looking at quantifying and improving memory bandwidth. There are 4 relatively simplistic tests that are done in this. The first one is simply a copy from one location to another. The second one is a scale, which a copy with a multiplier. The third is a sum, where you're adding essentially 2 blocks of memory together and putting that result into a third. And the final one is a combination of those called triad. For the purposes of time and the sake of simplicity, I'm not going to go through the gory details of each of these 4. Many people who are looking for one measure tend to use triad. So for the sake of simplicity, I'm just going to use triad. Going back to how do I know I have a good result with this test? Results are published on the University of Virginia website. I have to say they're sporadically published. They're not necessarily always up to date, but at least it's one of those ways of saying, hey, I just measured the stage. How reasonable is this measurement? They tend to be sort of the best ever numbers reported as opposed to everyday numbers. By default, it must be built, and by default, it runs 1 thread for every CPU that it can see. There is an available tool out there called publicly available called stream scaling. It's a script that actually examines the CPU type, the cache size, and comes up with optimal settings for running stream, which is a really good thing. And I'm going to show you first how you run it. In this particular case, I'm calculating the number of threads. You tell the test how many threads to use by setting an environment variable. Again, I'm setting up the file name using the same mechanism before. Then, in this particular case, stream doesn't really take any parameters, so you just invoke it, stream, and I use egrep to basically pull out that single number. And then, just to compare this with what you've already seen, to run the Sysbench memory test, you tell it the number of threads, you say the test equals memory, and then run. So here, let's compare and contrast these 3 measurements using the methodology I've described. So the first thing I want to point out is if our primary requirement was to pick any system that provided 20,000 megabytes per second, you can see of this list, the M2, one of the M2s is there, the others were not, and most of the other ones at least met that, with the CC2 8x large providing 55,000 megabytes per second. Now, how would you decide which instance to choose? There are lots of ways you could do that. You could say, which is going to cost me the least? I have other things going on where having more cores is better. I need more memory, that sort of thing. But in this scenario where I was looking for something that provided at least 20,000 megabytes per second, stream is telling me this. Now, this is the tuned stream triad where I use stream scaling to pull the result. And what that does is it tries threads 1 through n, where n is the number of CPUs, and essentially tells you what memory bandwidth you get with each, which means from an application perspective, you can use that to say, oh, well, if I use this many threads, I'm going to get the max throughput. Now, as mentioned before, geekbench is a black box, so you really have no control over how it runs the test. It is running the exact same triad test. What you can see comparing these numbers is that the numbers aren't the same. What does that mean? It means it's not tuned. It means you're getting the default values. So if you're looking for an absolute value, in this particular case, the only instance types you would choose are the C3 2x large and the CC2 8x large. Whereas in the first column, where I use the stream scaling script to find throughputs, I found there were a majority of these instance types would actually have met the goal. The last one I have to tell you is that the defaults for Sysbench are, let's say, different. And according to Sysbench, none of these instance types would have provided the bandwidth. However, caveat, Sysbench is actually doing an even simpler set of tests where by default it's doing sequential writes to memory. So if what you cared about was sequential writes, then triad may not be what you need, and maybe you need to use Sysbench and play with the defaults. And by play with the defaults, I mean heavily play with the defaults. Because what I've found is the defaults for Sysbench in general tend to be slightly meaningless because they were originally developed when CPUs weren't quite as powerful as they are today, or fast. The last topic, I have to apologize in advance. I could easily spend 2 hours on how to benchmark disk I/O, but I wanted to cover some of the main highlights, particularly in the choices you face on EBS, on EC2 with all of the variants. In fact, I'm thinking ahead of myself here. The first choice, if you wanted to test disk I/O on EC2, is what type of I/O do I want to test? Now, obviously, there are differences between using ephemeral storage in EBS, where you talk about availability and so on. You can use provisioned IOPS if you're worried about consistency of the performance. And on the new instance types like the C3s, where we have solid-state disks, or on the HI1, where there are solid-state disks, if you want blazing fast local storage, you may choose to use that, understanding what the characteristics are of that storage beyond just its performance. Secondly, when looking at disk performance, the question you have to ask is, what kind of measurement do I want to do? Do I want to do a single volume? Do I want to do a JBOD? Do I want to do software RAID? There are many different ways. Some tools are going to help you with this. Some tools won't help you at all. Finally, when it comes down to what you're actually going to measure, there are, fortunately or unfortunately, depending on how much time you have to do this, lots of things to think about. First of all, it's what type of access are you doing? Is it read or write or some combination? If it's some combination, what percentage read, what percentage write? Secondly, what access pattern? Is it sequential? Is it random? Finally, very important, and many people miss this step, you want to think about queue depth. What does queue depth translate into? Queue depth translates into how busy you're submitting the rate. Many people say, all I care about is IOPS, and I just need X IOPS. But if you ask them, do you want X IOPS at 400 microseconds, or do you want X IOPS at 1.5 milliseconds? They would say, well, of course, 400 microseconds. Then I would say, well, then you don't just care about IOPS, you care about IOPS and latency. And it's the same with bandwidth. So the broad categories are IOPS, latency, and throughput. So you can find, there's some good documentation actually on the EC2 website. If you do a search for EBS performance under documentation, you'll come up with a long list of recommendations, including how to run tests and so on. But I wanted to give you a simple guideline to measuring provisioned IOPS. Why am I choosing measuring provisioned IOPS? Because I've seen many customers who've struggled with either getting the IOPS they want, and it was simply a matter of how they were doing the testing. Remember, we measured this stage multiple different ways. Some gave us different results. The simple approach is to launch an EBS optimized instance. If you're going to measure PIOPS, you really want to use EBS optimized instances. Then you provision the volumes. Now, you can, with the wizard or with the API, do those both simultaneously, but I'm just making this a simple approach. Then you attach them. The guidelines in that documentation I mentioned talk about pre-warming the volumes. Why would you pre-warm? Unless what you're trying to measure is the performance in production of using a volume when it's just been provisioned, you're going to get a more reliable read when you've pre-warmed it. What is pre-warming? It means touching the blocks. And I'll show you a way to do that with FIO, which is one of the tools I'm going to talk about. But my previous point about latency, this is a graph that I produced with, don't worry about the complexity of the graph, just the two arrows. The leftmost bar, is the blue bar, is showing the Q depth for sequential read at 2,000 IOPS. Q depth of 1 is the blue bar, Q depth of 2 is the orange bar. So if I said all I care about is getting 2,000 IOPS, you can see that if you set the Q depth to 2 in this particular test, then you're going to be getting more than 2 times the latency than you have to get and still get the IOPS level. So Q depth is really important. So just to illustrate a number of different ways that you could measure and that I've seen people measure performance, one of my favorites, which definitely fits into the quick and dirty test, is someone takes an existing file, or a little more sophisticated, they use DD to create a file, and then they do a file copy. And they say, I'm going to measure the throughput of this disk by doing a file copy. You can calculate how long it takes to do it and say, I copied so many bytes in so many seconds. I have to caution you that it's not very precise, and it can be prone to all sorts of complexity. Second, a slightly more sophisticated way, people use the tool DD. I think one of the reasons they use it is it has to do with disks, and when it's done, it tells you what the throughput was, so it's all there. The challenge is it's not accurate from a variety of different perspectives. For instance, I'll show you some examples of where I ran DD. I ran DD of a 1 gig file, so I just used 0 bytes, created a 1 gig file, and I think it took 0.7 seconds to do that, and it told me that it was 1.5 gigabytes per second bandwidth. A, I happen to know the particular device was a PIOPS volume not capable of 1.5 gigabytes per second. B, I did the math and calculated how long it took versus how much data it copied, and the answer wasn't 1.5, it was 1.4 something. So it generously rounded up to 1.5. But it is easy to use and can be quick. So of the 3 variants I'm telling you, the most sophisticated, which is both good and bad, is FIO, Flexible I/O Tester. It's publicly available. The good part about this is you can test almost any kind of I/O pattern you want, including multiple volumes. It can do things, and the particular config file, which is where the complexity is driven here, does pre-warming. And it does it in a careful way to make sure you're really touching all the blocks. And I'm doing a very simplistic test, which is a sequential, what am I doing here? I'm doing a sequential write, and I'm using an I/O depth of 1, means a Q depth of 1. I'm doing 4,080 IOs per second. Now, these tests were all run on a 4,000 IOPS provisioned volume. And you may say, it's 4,000. Why are you doing 4080? Well, from my experience, when you drive slightly more than the provision level, you sort of get the maximum amount out of it. It's kind of like you go to the gas tank, you fill up your gas, and the machine cuts off, but there's still a little more space in there. You're not supposed to do it, but I like to fill it. Anyway, that's sharing way too much about my quirks. Sorry. Therapy again, therapy. So bringing this all in, I wanted to point out some of the problems with using copy, for instance. The first test I did was copy a 1 gig file from file 1 to file 2. And on this 1 gig provisioned, this 4,000 IOPS provisioned volume, it was actually 400 gigabytes in size. I had pre-warmed it, so there were no artifacts of the measurement. And I can tell you that the bandwidth of this volume is 64 megabytes per second. So anything that measures above that is probably not accurate. And so the copy, just simply copying file 1 to file 2, it took 17 seconds, and that told me that the bandwidth was around 59 megabytes per second. If I deleted file 2 and then did a copy of file 1 to file 2 again, it took 0.853 seconds. And it said that the bandwidth was 1,200 megabytes per second. Why do you think that was? Can anyone say cache? Yes. So there are artifacts of how you run these tests that can greatly perturb the results. You have to be very careful in both what the test does and how you run it. Then I copied file 1 to file 3, and file 1 is still cached, so again, it's really blazingly fast. Then I used DD, and the first test was using, as I mentioned, the 0-byte fill. And with 0-byte fill, the 1 gig file ended up, as I mentioned, taking 0.72 seconds. And it told me that I did 1.5 gigabytes per second, but if you do the math, it's actually 1.419.01. Okay, stop. Then I did a U-random. Now, obviously, writing random bits versus writing 0 fill are very different workloads. In this particular case, it took almost 80 seconds, and the measured throughput was 12.84 megabytes per second. Why do you think the bandwidth was only 12.84 megabytes per second? It wasn't the disk you were measuring, it was the ability to create random. So if you're trying to measure disk performance, U-random ain't the way to do it. Finally, looking at the FIO test. Now, I didn't go into detail about the config file, but this test literally ran for 30 seconds. So it was not a very thorough test. It takes a while to get things up to speed. But it measured roughly 61.5 megabytes per second. And I can show you in the next slide. I was asked to help out for a blog that Jeff did recently, sort of demonstrating testing at scale. So this is a 12-volume test with 12 4,000 IOPS provision volumes. And I ran a sequence of read, write, and read-write tests. And the flat bar line is 64 megabytes per second. So basically, I was able to drive 12 volumes simultaneously at max bandwidth. And I bring this up mainly to show that with FIO in particular, you can do some very sophisticated tests. If that's what you need, it's going to be much more accurate than the others. So I have a brief summary here, and we have a brief amount of time for probably a couple questions. But all of the stuff I threw at you in the hour you were gracious enough to spend with me this morning, you want to choose the best benchmark that represents your application if you can't use your application. You really need to understand what best means when it comes to looking at the results and telling you, is this a good test? Is this a good result? It's really important to run enough samples to quantify variability, particularly important in the cloud when there are lots of layers of abstraction, particularly important when you're running tools you're not used to make sure that the artifacts you're measuring are not part of the tool as opposed to the thing you're trying to measure. You really need to understand what a good result looks like, having a baseline, having a result someone else has run that you know is on a similar type configuration, running multiple tests to say, does this really make sense? Finally, keep all of your results. I can't tell you how many times I've gone back and needed my results from previous tests that had nothing to do with what I was trying to test. It saved me so much time to keep information about not only how I ran the test, but what the test was, and most importantly, the results. I have a database that keeps years of results in it, and I can do lots of wonderful SQL queries to pull it out. So, in the time that we have left, first I want to thank you. Secondly, I would appreciate it if you would fill out a survey. One of the reasons I'm here this year is I asked people to do that last year, and enough people were either caffeinated enough or that they appreciated what I talked about, or maybe it was the bribes. Whatever it was, they liked it, and so they asked me to do another talk. And so in the time we have left, which is about 3 minutes, so probably 1 or 2 questions, I'll answer questions, and then I have to vacate. I'll be outside, and we can go somewhere else if you have more questions. So any questions?